So in this video, we're going to be looking at electrochemical cells, a specific example of one, which of course is going to be a fuel cell itself. Now you might have come across this before, but just in case you haven't, basically we've got a reaction between some type of fuel itself reacting with, of course, an oxidant. Now that fuel is normally something like hydrogen or a hydrocarbon or some type of alcohol. A common example of one is of course going to be methanol, and we're reacting that with a common oxidant which is readily available, and that's going to be of course oxygen itself in the air. Now the whole purpose of this is to actually take our chemical energy and convert that into electrical energy, which we can use to power motors and to power cars and things like that. Now fuel cells, they're going to be different compared to conventional storage cells, which we've already come across, and we of course know these as batteries. And the main difference actually between the two, of a fuel cell and of course a conventional storage cell, is that when we look at a fuel cell, the fuel and the oxidant, we must supply that continuously, whereas of course in a storage cell that energy is already stored and we don't actually have the same process involved. Now for a hydrogen fuel cell, this is one that you need to be aware of. You actually take hydrogen as your fuel source, and you're going to be reacting that continuously with of course your oxidant, which is going to be oxygen. You only end up forming one product, which is going to be water. Water is the only product from this actual reaction itself, and you've seen an example of this in something like a hydrogen fuel cell car. You might have come across the Toyota Mirai, which of course is powered by hydrogen. So yeah, moving on then, what skills do I need to be able to kind of show in the exam? Well, the first thing is you need to be able to recognize the two different types of catalyzed hydrogen fuel cells. You've got alkali and you've got acid as well. You need to be able to balance some half equations based on this. Recall of course the transformations as well, that you can balance the half equations from the first place and then form an overall equation in terms of that as well. So yeah, I've got of course an alkali catalyzed fuel cell to begin with. We're going to end up with two processes taking place. One of them where we've got our oxygen, and that's going to be forming of course our hydroxide ions at one electrode itself. Now if I were to look at this, I need to think about this in terms of H, as we did before, where we of course balance the atoms to begin with. So I put 2 there to balance the oxygens. Then I'm going to balance the actual electrons. If I look on the right hand side, I've got -2 for oxygen. Over here I've got 0 0, so I know I must be gaining 4 electrons, 2 electrons per oxygen atom itself. So yeah, there's our electrons done and dealt with. What about my charges? Well, on the right hand side I've got a 2- charge overall. On the left I've got a 4- charge overall. So in terms of that, I know that I can only make one side more negative because I've got alkali conditions. It's alkali catalyzed, so I know I can only use OH- in this case. So in that case, right, I will end up with another 2 lots of hydroxide over here on the right. So there's my actual charges balanced. What about water to balance the actual hydrogens? Well, in this case I've got 4 lots of hydrogen on the right, so that's going to be 2 lots of water molecules on the left hand side itself. So that's their balance. Now I am going to clean this up a bit, so I end up with of course getting rid of all of this. We're left with of course 2 lots plus 2 lots of hydroxide. So overall we've actually got here 4 lots of hydroxide being produced from 2 lots of water, 4 lots of electrons, and oxygen itself as well. So yeah, what about our second half equation? Well, again, you need to remember this transformation as well, where you're going from hydrogen and you're going to be ending up forming water from this. So you're going to end up with of course H again. In terms of the steps, you're going to end up with of course balancing the atoms to begin with. Does it balance? Yes, it does. Hydrogen balances. What about the oxidation states? Well, you've got 0 0 here and you've got +1 here. So in that case, you know of course you're going to be losing 2 electrons, so you're going to have your 2 electrons on the right hand side. Now in terms of these, you can see the top one's going to be oxidation, the bottom one's going to be reduction itself. So yeah, our electrons balance. What about our charges? Well, I need to add some hydroxides here because I've got 2- on this right hand side, 0 on this left hand side. I can only make one side more negative, so I'm going to balance this side here by adding 2 hydroxide ions itself. So there's my charges balanced. What about my water? Well, in this case I've got 2 times by of course 1, which is going to be 2 lots of hydrogen in hydroxide, and then I'm going to end up with +2, that's going to be 4 hydrogens. I've only got 2 hydrogens on the right, so I need to have 2 lots of water itself to make that balance, and that balances just as it is itself. So yeah, I'm going to clean this up now, because in terms of my actual equations I now need to combine them. I need to multiply them first, if I were to look at the number of electrons, I can see over here that I've got 4 electrons here, 2 electrons there. So this equation here, I need to multiply it by 2 to get the common multiple the same. So in this case, I'm going to end up with 4 lots of hydroxide. I'm going to produce, of course, 2 lots of hydrogen, and that's going to make 4 lots of water, and I'm going to end up with 4 lots of electrons itself. So yeah, the next thing that I need to do is, of course, combine these two equations together, where I've got equation 1, equation 2, and I'm going to say that these are all going to be my reactants plus these, and then these are all going to be my products plus these, and I'm going to cancel them down afterwards as well. So yeah, I've got in that case 4 lots of hydroxides, and that's going to react with 2 lots of hydrogen. It's also going to react with 2 lots of water. We end up with 4 lots of electrons there as well, and that's going to react with, of course, oxygen. Don't forget oxygen. And then we end up producing 4 lots of hydroxide. We also end up with 4 lots of water, and then 4 lots of electrons itself as well. So yeah, in terms of that, what can I cancel on either side? I can cancel the 4 electrons here, the 4 electrons there. Right, so that's going to leave me with no electrons overall. I can then cancel the hydroxides over here with those over there. Normally in these equations, you should actually end up with the hydroxides being the same on either side, because remember, it is a catalyst. It doesn't take part in the reaction. And then, of course, you're going to end up cancelling your water, where you've got 2 lots of water left over here. And then, of course, you've got rid of all of these waters over here. So overall, what have you got? You've got 2 lots of hydrogen, and that's going to be, of course, reacting with oxygen to give you, right, 2 lots of water itself. Now, in some cases, just be aware that they might actually give half the equation. This one is still going to be right itself. This is our overall equation. They're done. Yeah, so you get 1 mark for, of course, 1/2 equation, 1 mark for the other, and the final mark for this last equation itself, the overall equation, which will always be the same. So moving on, that's our alkali catalyzed fuel cell done. What about our acid catalyzed hydrogen fuel cell? Well, it's the same thing over here again, but in this case, our transformation is going to start with hydrogen going to H+. And when we actually do H on this, right, we need to think about this in terms of our charges. We balance it using H+. So yeah, starting off with our steps, do our atoms balance? No, they don't. I need to put a 2 over there. Do our electrons balance? No, they don't. I need to have, of course, a +1 oxidation state for the hydrogens here. So overall, I'm going to end up losing 2 electrons. There's our electrons done there. Our H pluses, our charges on each side balances. We don't need to worry about that. And then, of course, we don't need water itself. There's that one done, nice and easy. Looking at the next half equation then, I've got oxygen, and that's going to be reacting to 4 water. So this one's a bit trickier, but again, we follow it in terms of H, where I've got the atoms. Are they going to balance? No. So I put 2 there to get the 2 lots of oxygen on the right hand side as well. The next one is, of course, our electrons. I've got 0, 0 here for oxygens, and then I've got over here -2, -2. So I know, of course, I've gained 4 electrons itself. The top equation is oxidation, and we know the bottom one is now reduction 2. So yeah, our electrons balance. What about the charges using H+? Well, of course, I know on the left hand side the charge overall is going to be 4-, on the right it's going to be 0, so I need 4 lots of H+ here as well. Yeah. What about the actual water, right? Does this balance? Well, I've got 4 lots of H+. That's going to be 2 times 2, 4 lots of hydrogen there. So that balances as well. The oxygens balance, our overall equation balances. Looking at the electrons though, right? We've got 4 electrons here, 2 electrons there. So after I've cleaned all of this up, right, I need to think about what I need to multiply. So if I were to look at this, right, I need to multiply this equation here by 2. So I get the lowest common multiple, which is going to be, of course, 4 and 4. So I end up with 2 lots of hydrogen. That's going to give me 4 lots of H+, and then it's going to give me 4 lots of electrons as well. Now I combine them together. So my reactants, which is going to be all of that, and then all of this, that's going to give me my products, which is all of this and then this as well. So I'm going to have, of course, 2 lots of hydrogen plus 4 lots of H+, and then it's going to be 4 lots of electrons. And then, of course, we're going to have oxygen as well. That's going to react together, and that's going to give me 2 lots of water, 4 lots of H+, and then our 4 lots of electrons. What can I actually cancel? Well, electrons cancel there, H pluses cancel there because that's a catalyst, and then of course we're left with 2 lots of hydrogen. That's going to react with oxygen, and we end up forming, of course, 2 lots of water itself, and there's your final equation there. right? So there's our acid catalyzed fuel cell. If you just remember these two transformations here, you can just do H in the exam, but since the new specs come out, they've not actually asked you to remember the actual transformations. Just be able to apply your knowledge in terms of balancing half equations to be able to do it in the exam. So moving on then, looking at some theory when it comes to hydrogen gas and using it in hydrogen fuel cells. Hydrogen gas is going to be extremely flammable. It's actually going to be explosive, and that's what makes it dangerous to transport, right? Now we need to be aware of 3 different ways that we can store it. One of them is of course as a liquid under pressure itself. Of course it's going to occupy a lower volume and it's going to be a bit more safer to kind of transport. Now there's 2 other ways that you can actually store it as well, right? These 2 ways, they sound very similar, but the difference is of course you've got adsorption, which is adsorption, and then you've got absorption, which is absorption. If you were to look at adsorption, what you're doing is of course you're taking a solid material itself and you're of course storing it on the surface of that solid material, so it's adsorbing, it's sticking to the surface. If you were to look at absorption, right, what you're actually doing is you're taking that solid material, but in this case, right, the solid is going to absorb, right, so the actual hydrogen is going to be absorbed like a sponge almost into the actual solid material itself, right? So there's the difference between these 2 over here. Now hydrogen itself, we already know it's very dangerous, and there are alternatives that can be used as well, right? Think about your hydrogen rich liquid fuels such as hydrocarbons and alcohols. A good example of one is of course going to be something like CH3OH itself, which reacts in a very similar reaction, but you end up producing carbon dioxide and water instead. That one of course it's not going to be as environmentally friendly as of course burning something like hydrogen in a fuel cell itself. Now a good thing about most of our actual alcohols and our hydrocarbons, generally they're going to be of course liquids. So if you were to look at stuff like petrol, if you were to look at ethanol, these substances, they're going to be liquids and they're going to be easier to store and they're going to be easier to transport as well. Now if you were to look at it in terms of methanol, right, the example that we've drawn out over here, we can actually generate this from biomass as well as ethanol as well. So that might be of course a more renewable way of synthesizing this hydrogen rich fuel itself. So yeah, looking at our advantages in terms of hydrogen fuel cells, we know of course when we deal with hydrogen fuel cells we end up producing water only as our main and only product, which of course we know water is of course less harmful compared to carbon dioxide. Although it still is going to be a greenhouse gas, it's not as an impactful one compared to something like CO2 itself. Overall we end up producing less CO2. Of course it's not going to be CO2 free. The main reason why is because how do you actually make the hydrogen in the first place? Normally it's something like electrolysis of water and you end up producing hydrogen gas, or let's say some type of decomposition of a chemical, you can produce hydrogen gas in that way as well. But overall you're going to be using kind of electricity, kind of fuel to transport this hydrogen itself around. And the final advantage is of course you end up with greater efficiency itself in terms of the actual energy being converted from chemical to of course electrical.